For this chapter, we're going to go through how a low mass star runs out of fuel and eventually will quote-unquote die, and do the same for a high mass star. So first of all, let's be clear about what we mean by low mass and high mass. So low mass is going to be anything less than 2 solar masses, so anything twice the mass of our sun. High mass is going to be anything greater than 8 times the mass of our sun. And intermediate, well, is in between the two. We're not going to actually go through the intermediate mass star. We're only going to go through the low mass and the high mass stars, and I think you'll find that to be enough information. So what's going to be driving each of these stages is the balance between pressure and gravity. Sometimes there won't be a balance. And what's providing the pressure is the fusion and the hot gas. So if you're running out of fuel for fusion, you're going to affect your pressure, you're going to affect your balance. So let's go through all of the stages. So as we're going through all of these stages, I suggest you flip towards the back of your chapter and find a full page figure. The full page figure organizes it really well. I actually would suggest reading the chapter starting with that figure and then getting into more of the detail. Okay. So let's get into the stages of evolution for a low mass star. Okay. These are my little pie charts describing a slice of the sun. So here's the surface of the sun, and it slices down into the core. Alright, it's obviously not to scale. I've left a note that the surface of a main sequence star like our sun would be yellow, technically whitish. Right? And our sun right now as a main sequence star is stable because of the solar thermostat. The sun is mostly hydrogen, so I'm going to color these yellow to indicate hydrogen. And for the core, I've left some F's here to indicate fusion. Alright, so here's the key. Most of the star is hydrogen, and in the core you have hydrogen into helium fusion. Okay. The main sequence phase takes up about 90% of the star's life, and remember that lower mass stars have longer lives. The main sequence phase is stable because of that hydrogen fusion in the core, because of the solar thermostat. Alright, so this is the phase that pretty much defines the star's life. Right. So, when we end the main sequence phase, we're going to start the red giant phase. So let's talk about what causes the red giant. Right. So, you had that core, and it was hydrogen into helium fusion. And that went on for about 10 billion years, making more helium, making more helium, making more helium. Eventually, I have to color code this blue for helium, because now it's mostly helium. Okay. So this helium core is going to be incredibly hot and incredibly dense. And you still have hydrogen fusion going on above it. We call it shell fusion. Imagine it a shell wrapped around a helium core. Since there is no core fusion going on, the solar thermostat is broken. There's no way for the core to expand itself to balance out its own temperature. Right? So this core starts shrinking, getting compressed, and that's going to heat it up. And as this core heats up, it'll make the shell fuse even faster. And this fusion is going to dump in so much energy into the star that it's going to push the outer layers out. And remember, the light and the energy is trapped in the bulk of a star for a very long time. So the heat can't just get away really quickly. It's trapped in all this material. So all it can do is push out on the outer layers. So take a second to notice that because the core is shrinking, that makes the surface expand. It's a little bit counterintuitive, right? But the core shrinking makes more fusion. That extra heat pushes the outer layers further out. And so the surface expands. And just because this gas right here has to expand and it's not getting any of this trapped energy from down below yet, the surface also cools and it looks red. So the red giant phase doesn't last horribly long, 9% of the star's life. Here's a little bit to scale. If this is the sun as a main sequence, this is what the sun would be as a red giant. Just because the outer layers swell up so incredibly huge. That's why I have not to scale written by all of my little pie diagrams. Even though the surface is cooler, there is a lot more surface, and so you can get more light out. So a red giant is actually much more luminous than a main sequence star. So you've got the red giant with that helium core that is getting compressed and heated. At some point it actually gets hot enough to start helium fusion. So now I've got some F's down here to indicate fusion. Okay. So this is going to be called the helium burning star, or the helium fusion star, but it has two sources of fusion. It has helium in the core and hydrogen in a shell. Right. Because the core is now fusing, it can re-expand itself and fight against gravity. That'll cool things back down a bit. That'll cool this shell off a bit. Overall, what helium fusion does is it brings the star back into control. And so the fusion rates back down a little bit, and it allows the outer layers to shrink back down almost to their main sequence levels. So the surface is going to contract a bit, and it's going to heat up, so it's going to look yellowish again. Now that you have fusion in the core, your solar thermostat is going to try to take over again. But now your thermostat has to control two different types of fusion, hydrogen fusion and helium fusion. So it ends up actually overcompensating. And so a lot of helium burning stars pulse. They get brighter and dimmer, brighter and dimmer, brighter and dimmer as the solar thermostat tries to fix it, overshoots a little bit, brings it back under control. Overshot it a little bit again. Okay. So a lot of these helium burning stars are really interesting. Before we get to the next phase, let's just take a look at what this was doing on the HR diagram. Okay. While it was main sequence, it was stable. Okay. And then the core was shrinking, causing that shell fusion to go crazy and the star to expand. So that's what's happening here, is the star is expanding, expanding. It's looking redder and brighter because of that expansion. Okay. There's your red giant. And then once that helium core turns on, brings stuff back into control, your star is allowed to shrink back down and the surface will heat up a bit again. So there's your helium burning star. Helium is not the most efficient fuel, and the star doesn't have near as much of it. So this phase only lasts 1% of the star's life. Right. While it is here though, it's about 100 times more luminous than the main sequence star. Right. So you can see it's more luminous. That helium fusion made carbon, but eventually that carbon is going to add up. So let's color code this core now to be carbon. And you have the helium fusion now moved to a shell around the core. And above that you have another shell of hydrogen fusion. So we call this phase the double shell burning star. So very similar to the red giant, the core has no fusion. So it's going to be shrinking and heating, which is going to shrink and heat these layers, which drives their fusion rates out of control. And all that extra energy is going to get dumped into the bulk of the star and push the outer layers up. So the star is going to get really huge, and the surface is going to expand so much that the surface is going to look red again. Your double shell phase doesn't last very long, a few million years, which is really short for a star. That huge surface is going to emit a lot of light, 10,000 times more luminous when it's in this phase than it was as a main sequence. And while that star is so huge, its outer layers are pretty far away from the core of the sun, so gravity doesn't have a really tight hold on those outer layers. And so a lot of the outer material can drift off into space. So these would be called winds, particles being lost by the star. And as the star is dying, running out of fuel here, it has some really impressive winds. It's losing a lot of material. The next phase is called the planetary nebula phase, and it's basically where the two shells of fusion put so much energy into the gas that the gas pressure is much greater than gravity, and so these outer layers of the star just take off into space and leave the core behind. Your hot core, and it's going to be hot enough to glow in the ultraviolet light, so this core shines light on these gases as they're leaving, and they're really, really pretty to see. So let me show you some planetary nebulas. Here's the Eskimo Nebula. Here's the Spirograph Nebula. Right? So these don't last very long. The gases are still drifting away from the star, but we might see one in the sky for about 10,000 years. The reason why they're called planetary nebula is when people were looking through a telescope, planet meant it looked round. So Jupiter looked round in a telescope, Saturn looked pretty round in a telescope, and these nebulas also looked round in a telescope, so that's the planetary part of it. Historically, nebula meant fuzzy. So these looked like fuzzy round things, so they called them planetary nebulas. Here's the Ring Nebula. This is much, much, much prettier than it would look to your human eye. To your human eye, you'd see a little kind of smoke ring, and you'd look at me after you'd look through your telescope and you'd say, "That's it?" I say, "Yes, that's it." The last phase for a low mass star is called a white dwarf. And the white dwarf is just a new name for this carbon core. And basically what a white dwarf does is it cools forever. That's what it does. It's just going to get cooler and dimmer as it orbits throughout the galaxy. We're going to talk about white dwarfs more later, but for now, let's just say that it'll take billions of years for the core of the sun to cool off, and it's going to be about the size of Earth. Okay? Don't picture Earth orbiting this thing at all, because Earth is going to be long gone. Earth is probably going to get eaten by the sun when it's a double shell burning star. So let's use this animation and talk through the phases as they happen. So we'll start off with main sequence. Red giant, right? So there's that shell fusion that's not stable. Comes back down. That's the helium burning star. It's got the core helium fusion and a shell of hydrogen fusion. Double shell burning star. Notice the radius of this thing. The radius is 1 AU. That's Earth's orbital radius. The Earth will probably be eaten by the sun at this point. It'll have already been baked. Don't worry about that. We'll already be dead or gone. But here, Earth gets eaten. Poof! Planetary nebula gases leave, and then all you have left is the white dwarf, which is cooling and dimming with time. So we can come back to the ATAR diagram. We already talked about the main sequence and how it gets bigger and brighter as it becomes a red giant, how it hops down here as a helium burning star. But now we can keep going. Once it runs out of helium in the core and it turns into a double shell burning star, it works its way up. More extreme fusion, until it reaches as high as it can go. And then those gases get so much energy that the outer layers of the star just poof, poof away, and it'll basically hop from being a double shell burning star down to a white dwarf. And your white dwarf is going to start off as bright as it can be, pretty darn blue, glowing mostly in the ultraviolet, but over time it cools and gets dimmer. At some point you could call it a black dwarf, but why bother?